Move you guys around a little bit. That's in the way. Move this over here. Okay, terrific. And, oh shoot, that got in my way. Okay, cool. Hopefully, if you saw my email today, I'll give you guys a minute to deal with this if you didn't. What I did is I wanted to reapproach some of the stuff that we talked about on Tuesday. So I've uploaded a set of slides that we're going to go over today, but I put them in a PDF form. So each page is like 2 slides, and it parallels what we did, but it's slightly different. So if you wanted to take notes, you're welcome to go grab that off of Canvas, and you can print it out. You can write on it electronically, whatever you want. They're your notes at this point. But those are the slides that we'll be working with today, so that you can try to follow a little more closely, and we don't just go completely off of the ones that I provided you for the whole class. So we will still be talking about systems and control volumes, Reynolds transport theorem. We'll go back to kind of rederive this in a slightly different way. A couple of announcements. So no class next Tuesday, and next Thursday. I hope I said that. For next Tuesday, though, go ahead. We're going to just move the schedule up a little bit. Just go ahead and read section 5.1, and we're going to talk about what happens when we have control volumes that are moving. Because now we have to start thinking a little bit about 2 different velocities here. If we took our control volume, moved it, we need to consider that velocity as well as the velocity of fluid perhaps moving out of it. And the classic example of that is the image you can see right here on this slide, which is a sprinkler head spinning around and spitting out water, right? We know that there's some velocity to the head of the sprinkler spinning, and then there's another velocity of the fluid coming out. So we can calculate that. And you may look at sprinklers very different from here on out, which is totally fine. But not necessarily the goal of what we're trying to do. So I will get homework 9 posted tonight or early tomorrow. I should have time later today to do it, probably before about 5 p.m. So we should be in good shape. But I'll send you an email when I get it posted and ready to go. And like I said, you'll have 2 weeks to work on it. So, Emma, any questions popping up? Are we good to get started?
No, you're good.
Okay, terrific. Thanks. Excuse me. Okay, so we talked a little bit about the Euler and Lagrangian differences before, and I just wanted to redefine them a slightly different way. On the right-hand side, what we see is like a smokestack, steam coming out, whatever. It's some kind of vent out into the natural world. And if we are Euler, we think about a process or a perspective in which we are fixed in space as an observer, and where what we see through time is material changes, meaning that we have a view of the world and we see through some lens, meaning some perspective we've got, says, hey, I see things moving faster or slower in different parts of this field of view that we have. The Lagrangian approach, so we could imagine then, let's just take the smokestack, we could think about sort of looking at it from our perspective just as we are right now and thinking about how velocities change perhaps across the view that we have. The Lagrangian perspective is a little different and says, I'm going to go to this particle and I'm going to evaluate how it speeds up or slows down based on the way in which gravity or other factors are somehow influencing the way I move. So now we take a perspective where we are moving in space, and it's all the same material, right? We have one particle that we are tracking. So we are tracking how that thing is moving, and we're not looking at necessarily all the other particles coming through our field of view. Okay? So oftentimes, as I indicated on Tuesday, we see that there are like a change with time in our Lagrangian approach, and we have some initial conditions that are set, and then we change with time from those. Okay. Okay. So we talked about this material derivative, and I want to do a better job of kind of introducing us to this. So for an acceleration field equation, we could say something like the acceleration vector, A bar, is equal to some dv dt, and I'm using capitals here to indicate that I care, in this case, what I'm using shorthand for all of the velocity components in all directions, okay? So what we could write this out to be then is that this would be something like del v del t plus a u del v del x plus some v del v del y plus a w del v del z. Okay, so we've taken this big derivative here, this proper derivative, capital D's, and we've equated that or given it some meaning in the sense that we are going to assess what's going on in all directions. And so we use this term here, this d of whatever. It could be velocity, it could be mass, it could be, temperature. This is what we call the material derivative. Okay, so when we defined this last on Tuesday, I think I had one of our equations set up. So it looked like more of this, some sort of, what do you call it? Already expanded, right? That it was defined in some way by a bunch of stuff on the right. The reality is the right side of what we have, for example, for looking at acceleration is the material derivative of velocity vector, right? Where the velocity vector may have x, y, z components and it might be changing in time. And so we have these components that we talked about a little bit. We'll redefine them here as we did on Tuesday. Now, another way of writing this, if we're not just talking about acceleration, is to write this in a slightly different way where we do have a couple of generic things on the right-hand side. So the left-hand side remains d, capital D of whatever dt. So perhaps this is, could be velocity, it could be, again, temperature or something like that, heat content. And then the right-hand side, as we indicated before, has a temporal component, and then it has some components that are related to variability in space here. Okay, so the v vector here, of course, could have x, y, and z components. The gradient component is simply giving us it says that it indicates that we are going to take the velocity vector and take the dot product with the gradient in all three directions of whatever our thing is: velocity, mass, temperature, whatever is in parentheses. So this is the very generic form of this equation. But let's write these things out. So on the right-hand side, this v bar or velocity vector times the gradient is dot product of the velocity and gradient vectors And ultimately, this gradient vector of whatever our characteristic is that we care about for a fluid, for a flow, looks something like this. Del x times the I hat unit vector plus del of whatever it is, del y of the j hat unit vector plus del, again, of whatever it is, del z of the multiplied by the k hat unit vector. So this is ultimately what we would call a gradient vector. Okay? So when we combine these and we have the velocity vector dot product with our gradient vector of whatever it is, we ultimately can get rid of those unit vectors and end up with u being the velocity component in the x direction multiplied by this del whatever del x, right? So this is just a open parenthesis there, plus v del of whatever del y plus w del of whatever del z. Okay? Sorry to cram that in there. I guess I could have given myself a little more space. But in any event, when we combine these things, that second this second term on the right-hand side of the material derivative is key in sort of providing us with the combination of the velocity forcing things to change in space, right? Moving a particle or some of our system from one place to another. And then, of course, the gradient vector giving us some gradient in 3 dimensions of the condition that we care about, the characteristic we care about. Again, within these empty parentheses could be mass, could be temperature, could be heat, something along that line. Okay? All right, just want to make sure everybody's got that. Okay, so there are 2 primary terms in the material derivative, right? What we saw was a del of whatever del t. So this is the first term on the right-hand side of the equation, and this is termed the local derivative and it represents what we would call the unsteadiness of the flow, so changes across time. Sorry for this gap, I think a tab got in there, but it equals 0 for steady flow. So in other words, if something like, because we're dealing with incompressible fluids, for example, we would say that the change in density with time is equal to 0, right? So del rho del t is equal to 0 because we expect that there are no changes with time. And so that's a steady flow property. The second part of this on the right-hand side that we explored on the previous slide here was this velocity vector multiplied by the gradient vector of whatever this thing, this characteristic is that we care about. And this is what we call the convective derivative. It represents that any flow property may vary in space. I thought I had something to write in there, but it looks like I left the words in. So that's our convective derivative. So there's a local derivative and a convective derivative. And convection is often a term that is used to infer movement, velocity. That's why convective includes that velocity vector. The local just includes the temporal component, okay? All right. Okay. So here is a a reducer in a pipe. So a pipe is coming from, flow is moving from left to right. It goes through this little reduction, and then there's a flaring back out as we go from point number 2. So this is point number 1 here. Number 2 is right here. And point number 3 is down here, right? And as we get down to 3, we get, you sort of flare back out to a more uniform cross section. And as is indicated here, we have uniform velocities across each cross section. So we're not accounting for any friction with the walls, that kind of thing. But we see that the velocities should change, right? If we look at the x component of velocity, so a one-dimensional velocity component going from point 1 to point 2, because the size, the diameter of the pipe decreases, we expect V2 to be greater than V1, right? So here we indicate that the velocity at 2 is greater than the velocity at 1. So I don't know, I guess those arrows are slightly bigger, but they're certainly more dense anyway. And then as we get to 3, we see that V3 is equal to V1, meaning that this cross-sectional area or diameter must be the same as it is at 1. So D1 equals D3, let's say. And both of those are less than the velocity at 2. Okay, so that's what we're being told here. And so we're just going to note, because, for shorthand, I'm just going to use BEC, because the velocity changes in space, this would be a G, changes in space, oh goodness sakes, that's in space. So in other words, with the x direction, the convective derivative within the material derivative will apply. Okay, so if we were working with the material derivative, we would definitely use the second term on the right-hand side of the equation, because regardless of what it is we're looking at, whether it's like, you know, mass or temperature or whatever we put in our parentheses, the velocity vector is changing, right? From 1 to 2, it increases, and from 2 to 3, the velocity increases. So we would have to have some function to describe that. However, for steady flow, so steady invokes time. So for steady flow, which is no change in V with time, the local derivative does not apply. Okay, so that is the first, that's in reference to the first term on the right-hand side of that material derivative equation. Because del T is in the denominator there, all we care about is what's changing with time. And velocity here, we're not given any information about a change with time. It is changing with space, okay? Make sure everybody gets that written down. And then we're going to go through, let's see, do I have two? Oh, just one example. And then after that, we'll, I think do I have 2 examples lined up back to back? I think maybe I do, so. Okay. So, this is a little bit like the one, I think, part 2 problem that you had on the homework due today. Temperature of the exhaust of an exhaust pipe can be approximated by the following equation, and that equation is move you out of the way. T, the temperature, is equal to the initial temperature T naught multiplied by 1 plus A e to the bx minus bx, pardon me, plus 1 or multiplied by the quantity 1 plus C times the cosine of omega t. So if we're given some initial conditions, T naught is equal to 100 degrees C. We're given that A as a constant is 3, so that goes here. B is 0.03 per meter, that goes there. And C, right here, is equal to 0.05. We're also given that omega is equal to 100 radians per second, okay? So if the exhaust speed is a constant 3 meters per second, okay, so now we are thinking about the rate at which this fluid comes out of the exhaust. What we're supposed to find is the time rate of change of the temperature of the fluid particles at x equals 0, t equals 0. So in other words, just as we are emerging from the pipe, from this tailpipe, how is the temperature changing for our fluid particles? So ultimately, as you can expect, we're going to have to take the derivative of this equation, and we're going to apply the material derivative here. So we're going to end up probably taking a temporal derivative as well as a spatial derivative. Now, we're only given information about the exhaust speed coming out at 3 meters per second. When we're only given that one velocity, we can immediately think, well, it must just be in one direction, right? And that's not too unfair, right? If we think about an exhaust pipe, if you look at it, it should be shooting the exhaust straight out, more or less. So we can think about this as a one-dimensional problem. Now, as soon as you enter a wind field, of course, and you're putting, this exhaust that is ultimately a gas out into a field of moving gas, right? Of air, if it's behind a car and it's moving, for example, or you've got some crosswind, of course that plume is going to go in some other direction. But for now, let's just take a look at a very simplified situation to apply our material derivative understanding to figure out this time rate of change of temperature of the fluid at x equals 0, t equals 0. Okay. So let's start with our new best friend here, material derivative. Oops. Okay, I goofed it up right off the bat. That should be in the denominator. The change in temperature with time is equal to these two components, as we said, the local derivative, del capital T, del little t, so change in temperature with time, plus a convective component, which is the velocity vector times this gradient vector of, this should be temperature here, okay? I didn't need those parentheses actually, but I put them in there just to keep everything on the right-hand side of the plus sign together as a single term. Okay, now if we expand this out, as we had done 3 or 4 slides ago, we would have the local derivative would stay the same, and then we would break this piece up, the convective derivative, into 3 components. So u del t del x plus little v del t del y plus the lowercase script w here, del t del z. But the only information we're given is a u value, so one velocity here. And we start, usually if we're only given one, it's about x. I suppose that would be different in the case of like trying to track a raindrop falling, right? That would be vertical rather than horizontal. But in this case, we can think about an exhaust pipe being horizontal, and we have a horizontal velocity. So this term goes to 0, and this term goes to 0, and we just need the one-dimensional form of the second, the convective derivative, essentially. Okay, so, and recall that we are given u is equal to 3 meters per second, v is equal to 0, little w is equal to 0. So we have a value to stick in for u. Now we need to think about these derivatives. Okay, so let's take the first piece of this and calculate. Tell you what, just to try to be a little bit clearer for your own notes. Oops, what do I want to do here? I'm going to change the pen color. So I'm going to go with blue and just say, let's first calculate this del T, okay? So the change in temperature with time means that we're going to take that equation from the previous slide and take the derivative of it with respect to time. So this is now equal to del T of that whole equation. So it was T naught times 1 plus a e to the minus bx. We have values to put in here, but we can just deal with the constants for now, times 1 plus c times the cosine of omega t. Okay? When we take the derivative with respect to time, we get t naught as a constant out in front there, multiplied by 1 plus a e to the minus bx, because there's no time component in that first bit at all. And then we multiply by this by minus c times omega times the sine of omega times t. Okay? Yeah. So there's our derivative with respect to time. I'm going to hold off on putting in our constants just yet until we put all the pieces together. Okay? But we've got this worked out now, and we're ready to substitute it in after we figure out this del T del X. So, change colors again. We'll work the del T del X. Oops. There's green. Okay. So, oops, I guess it's not that one. It's actually this guy right here. So, del T del X, that's a little light. Hate for you guys to not be able to see that. Let me go to black. Del T del X. So now we're just calculating this derivative real quick. Is equal to del X of T naught times 1 plus a e to the minus bx, where now this will obviously come into play for our derivative. And then we multiply by 1 plus c times the cosine of omega times t. Right, and so when we take this derivative, we get T naught is equal, T naught times a negative a times b times e to the minus bx multiplied by 1 plus the times c, I think, oh yeah, okay, times c times the cosine of omega t. Okay. And then we can put all this together. So I'm going to give you guys a second to catch up. And on the next slide, we'll put all this these pieces together. So we've got our del T del X and our del T del T, and we know what U is, and then we can start to simplify and substitute. All right. So we now have, let me go, I guess I'll go back to blue to put it all together. So the, dang it. I don't know why I needed to do that again, but anyway, dt is equal to T naught times 1 plus a e to the minus bx times minus C times omega sine of omega times t. And then we add, I think, well, yeah, I'll just do it this way to make sure I have enough room. 3 meters per second, so that's the U value, times T naught times minus A times B times e to the minus bx, and then multiply by 1 plus c times the cosine of omega times t. Close that bracket there. Okay, so now we can do the slightly tedious step of evaluating this derivative at x equals 0, t equals 0. And when we do that, we can plug in our we can eventually get to the point where we plug in that t naught. Real quick. Oh, I see. Yep. Okay. So when we plug in 0, we get, or x equals 0, t equals 0. Here, this is when we take e to the 0, we just get 1, right? So we're going to have t naught times 1 plus a times, and then when we take the sine of 0 time, we're going to end up with 0. All right, so this ends up simplifying quite a bit. And then, so that's our local derivative. And then we're going to add 3 meters per second times t naught, and then this minus ab times e to the minus bx. When we put in 0 there, we end up with we end up with just minus a times b here. And then when we put in a 0 for time, again, this cosine now goes to 1. And so we just end up with 1 plus c. Okay? So this whole term, as it turns out, all of this goes to 0 because of this 0. So we end up, and you can see why it's a little bit handy for me to work with the letters until we get to this point where we can put in all the numbers. We don't have to drag those numbers around. So 3 meters per second times, now t naught is 100 degrees C times a minus, let's see, where did that come from? Oh, we said a is 3. So this is, I'm just going to put the minus in here, minus 3. And then b we said was 0.03. 1 over meters, I think it was, meters to minus 1. And then we multiply by 1 plus, that's curious, 1 plus 0.05, which is c, okay? So all of that comes down to change in temperature with time at x equals, sorry, that should be an x equals 0, t equals 0 is equal to minus 28.4 degrees C per second. I left, oh no, these meters canceled with these meters, the per second stayed in there, and there's the degree C. So the units all check out as well, okay? So there we go, the material derivative helped us find this gradient, this change in temperature for exhaust coming out of an exhaust pipe. All right. Any questions on that? Okay, cool. Anything come up, Emma? Okay, terrific. All right, another example. The temperature distribution in a fluid is given by T equals 10x plus 5y. where X and Y are horizontal and vertical coordinates. So sometimes you get Y as vertical, right? It just means we're working in 2 dimensions anyway, in meters, and T is in degrees Celsius. So what is the time rate of change for the temperature of a fluid particle traveling A, so 2 cases now, A, horizontally with U equal to 20 meters per second, and V, remember this is velocity, the vertical velocity now, equal to 0, and B, a second case, where you're just moving vertically with U equal to 0, so we're not moving horizontally, and V, little script V, that should have been a script V, equal to 20 meters per second, okay? All right, again, we can apply the material derivative. In this case, we're amping it up a little bit, right? We're gonna go from 1 convective acceleration on the right-hand side, the second term on the right-hand side, to 2, all right? So we're going to have dt, so change in temperature with time is equal to del T, del T. So now the temporal component of change of the equation that we have, plus these 2 convective components, pardon me, U del T del X, so the horizontal direction, plus, and I'm just going to choose V. We could have done W and dt dz, but anyway, del T del Y, okay? And we're given these 2 cases where we know U and V, and we know U and V, okay? So we'll get to that in just a second, but first we need to take the derivative of that equation to be able to, in both in time and in space, to be able to inform the equation that we have here, okay? So the first thing that we'll do on the next slide here is calculate this first. Let's do red for this guy. All right, so del T, what does that come out to be? So the change in temperature with time for our function that we're given looks like this: del T of 10x plus 5y. Well, I don't see a T in there at all, right? So its change in time is 0. So there is no local acceleration for this particular solution. So that's helpful, at least simplifies things, right? Now let's change our pen color here. What was working? I think, let's see how bad magenta is. Let's see if that works for us. All right, let me go back to the previous slide and just note, so now we need to figure out this del T del X and del T del Y. I guess actually, yeah, we'll just do both of those and then we'll bring them in. So del T del X now is equal to del X of 10x plus 5y, and that derivative is just 10. And as it turns out, this comes out to be degrees C per meter. The reason we know that is in the given, we were given that temperature T is in degrees Celsius and that X and Y are both in meters. So that's just how that worked out. Now, I guess I'll keep the same color because that's what I did on the previous slide, the way I circled it. Del T del Y, similarly, we take del Y of 10x plus 5y. And again, we end up with something similar. In this case, 5 degrees C per meter, okay? So we now have, let me just check. Did I give myself another slide or not? Nope, okay, come back. All right, so now we can put it all together. So let's do that with, so for A, we said, what do we have? We had U is equal to 20 and V is equal to 0. So for A, D, the change in temperature with time is equal to, remember we said that the temporal component of this, del t is equal to 0. So this simply equals u del t del x. So just one component of our, well, actually for completeness, I'll just go ahead and write it out. Plus v times del t del y, but this we said is equal to 0. V is equal to 0. And u is equal to 20 meters per second. So this comes out to be 20 meters per second times, and then we bring this guy down here, 10 degrees C per meter. So that comes out to be a 200 degrees C change per second. Oh, sorry, per meter. No. Wait, what did I do? Oh yeah, per second, that's right, yep. So the meters cancel, and our change of temperature with time, given that we're moving at 20 meters per second, is 200 degrees C per second. Similarly, for the second set of conditions we had, del t or dt, change in temperature with time, is equal to, I'm just going to skip this part because u is equal to 0. So I'm just going to write this, it's just equal to v del t del y, and that's equal to, now in this case we have 20 meters per second times 5 degrees C per meter. The meters will cancel. We end up with 100 degrees C per second. Okay, so those are our solutions there. All right, any questions on that before we keep going? All right, terrific. Okay, so now let's get back into the conservation of mass. We recall that we're going to define this time rate of change of a system of mass is equal to 0. The mass change is going to be equal to 0. So the definition is the time rate of change of system mass is equal to 0, or doesn't change essentially. So we can write that as d m cis dt equal to 0, right? And we can define the amount of system mass as follows, which we had written before. So m cis is equal to the integral over however the system is defined, times rho dv with the, in this case now, this v has a line through it, so it's indicating volume, not velocity, okay? So rho, of course, is the density of our fluid. This dv with the line through the v is our differential volume, right? So what does this equation mean in words? What it means in words is the time rate of change of the total mass of the system is 0, or essentially mass is always conserved. Okay, now that's an easy concept. I mean, any of us should sort of agree with that on the face of it. The point of the next couple of slides then is to just rederive this and prove this to ourselves mathematically, okay? And from that comes the Reynolds transport theorem. All right, so we have a lot of everyday simple illustrations of mass conservation, whether it's filling a glass. We have a problem right now with our the water dispenser on the front of our freezer, door, refrigerator door. And when you go press it, it doesn't stop coming out when you pull your glass away, and just sort of just tinkles all over the floor, right? You just have this water like keeps coming out. But we have this concept of at least this glass from a mass balance perspective. It can only hold so much mass, so much volume, right? So once we fill that up, we can then think about exactly what happens to that system of fluid that we've put inside this. Similarly, we might be able to do that with the tank that is pre-cooling that water inside of our refrigerator before it comes out. Obviously, it's connected to a water line so that it will never run out. But the cold water, has a certain volume to it, and once that is all gone, you get warm water because the new water hasn't cooled down yet, unless you wait long enough. All right, so we can think about sort of some everyday illustrations of mass conservation, but ultimately, continuity or mass conservation is this integral balance law that we can analyze in terms of a fixed, non-deforming, control volume. And I'm just going to indicate CV as control volume, distinguished from CS, which would be a control surface. And the control surface is simply the outer boundary in 3 dimensions of the control volume, okay? So as we talked about before, a control volume, its control system is identified here in this red dashed sort of curve in this bend in this pipe. And our system of fluid is outlined in black here, entering on the left-hand side at some t minus delta t time, completely occupying it at time t, and then at time t plus delta t, we see it start to move out, right, on the right-hand side. So it's coming in at 1 and going out at 2. And so our control volume is the thing that is fixed and non-deforming. Our system is deforming in that it's got to, as a fluid, fill and somehow occupy the control volume, right? A fluid can do that. It can move around and take different shapes. Okay, so this figure above shows that the system and control volume at 3 different instances of time. We describe the conservation of mass in terms of control volume and control surface as follows. The rate of change, so I'm going to write this in a way that looks a little bit funny at first, but I'm trying to provide you with the English version of a mathematical equation that we'll write on the next slide. That's why I'm kind of bunching my words and grouping them in certain ways kind of as I go across here. So the rate of change of the mass of a system is equal to the time rate of change of mass within the control volume plus, I guess I gave myself a lot more room than I expected, the net rate of change or net rate of mass flow or exchange through the control surface. And remember, the control surface bounds the control volume. So it's kind of like saying, in and out of the control volume. You could say it that way as well. Okay, so that's the conceptual version of what we're going to write mathematically on the next slide. Okay?
And CS is control system?
No, a control surface.
Okay.
Yeah, thank you. Yeah, that would be bad. We don't want to mix up our system and our control volume. So glad you asked. Yep, control surface, which bounds the control volume. Okay, so what does this equation look like? So we can more formally express the text that we wrote on the previous slide with the following integral balance equation. And it looks like this. d dt of the integral over our system of rho dV, in this case the volume, is equal to del t of the integral over our control volume of rho dV. Okay, so that is our stored mass, plus the integral over the control surface of the fluxes that are occurring. Okay, so this is now rho times the velocity vector, capital V, times n hat dA. Okay, so what is n hat? Around our control surface, I'm going to change my pen color to red here. And around our control surface, everywhere that there is an opening, an entrance or an exit, we have what we call a normal vector. Okay, and this normal unit vector is just n hat. So on the upstream side, where we have the inflow coming into our control volume across our control surface, we have n hat working in the opposite direction as the velocity. Okay, but on the other side, on the outflow side, you can see that the two of them are going in the same direction. And this is part of the reason why on Tuesday I said, well, you're accounting for a negative here for the stuff that comes in. This is where that comes from. So let me identify this a little bit better. So the velocity vector times the dot product of n hat dA is the product of velocity component that is perpendicular to the control surface. Oops. And it should come out in I have some dimensions here that I don't trust. I think those are a bit wrong. I think I'm not going to write that. But in any event, oh, I see. Yeah, I see. This should be, yeah, that's right. This does end up in length cubed per time. And the reason for that is it's a velocity. Remember, the unit vector has no units to it, right? The velocity vector will. It will have meters per second or something like that. And then area, of course, will have length squared. So length per time multiplied by length squared gives you length cubed per time, all right? So there's one part of what we talked about above. The next part is to just indicate that this term overall is represents a mass flow rate through the control surface. In this case, through dA, and it's greater than 0 for flow that is out of the control volume or out of the control surface, and it is less than 0 or negative for flow into the control volume or into the control surface. Okay? And so I realized that's a little bit counterintuitive. If we were to think about this control volume as your bank account, you like to add money and have that number go up, right? You would add it. And then when it comes out, it would go down, right? You take money out, you see your balance go down. But that's not quite the way this tracking of our system works. You see, we've partly because of this vector notation, these normal vectors on the upstream end working against the inflow and on the outflow end working with the inflow gives us that reversal in signage than what you might expect. Okay? So now we can start to simplify. All right, so let's take this and try to simplify it a little bit. So first of all, we can express the control surface term, i.e. the second right-hand term on the right-hand side, in terms of mass flow rates. So in other words, just this integral over the control surface of rho v dot n hat dA can be equal, we can set that equal to the sum of the mass inflows mass outflows minus the sum of mass inflows. Okay? Recall that m dot is equal to rho times q, or equal to rho times v, the average velocity, times cross-sectional area A. And so this is a mass flow rate. And its dimensions are in mass per time, or mass times to the minus 1. Okay, so in general, all of this should work for any sort of fluid that we have, fluid system, that is passing through a control volume, right? We can account for it. Mass flux out, mass flux in, and whatever is stored at the current time. Let's take the specialized case of saying, you know what, our system is made up of mass, or is a fluid that is incompressible. And the system mass change with time has to equal 0. And of course, all of the mass of our system is represented with this simple expression. So we can express the conservation of mass as follows, which is to say 0 is equal to del t of the integral over the control volume of rho dv, that's volume there, not velocity, plus the integral over the control surface of rho v, which is a velocity vector, dot n hat, or normal unit vector, dA. And we've simplified this, right? On the left-hand side now, because we have said that dm, capital D, capital M, divided by capital D, lowercase t, is equal to 0, we are not changing our mass, then these two things have to balance each other on the right-hand side. In other words, whatever is stored, the change in time of the stored mass has to equal the flux, the net flux of mass coming through the control volume entrance and exits. So what does this equation simplify to for a steady, incompressible flow with one stream of a specific fluid? That's awfully specific, isn't it? Well, let's break this down a little bit. We said it's one-dimensional. So if it's one-dimensional, we only have to worry about V's occurring in one dimension. N hat's only working in one dimension. If it is steady, then this term right here, that term is going to go to 0 because that's a del t, right? And if it's incompressible, then that means that we have this situation where the mass has to be balanced. All right, so what does this mean? The next slide, what this means is for steady and incompressible flow, we say that del t, that first term on the right-hand side, the integral over the control volume of rho dV is equal to 0. And for 1 d flow of a specific fluid in a stream, we would then write integral over the control surface times rho v dot n hat dA is equal to, we said, the sum of the mass outflows minus the sum of the mass inflows, and this would basically be equal to 0, so that we could say that all of the mass outflows are equal to the sum of all of the mass inflows. And we could then expand these out and say rho out, A out, V, now velocity out, is equal to rho in, A in, times the velocity, mean velocity in as well. And we know that these two rows are equal to each other, so they cancel out. So what that means then is, A out, V out is equal to A in, V in, and therefore Q out, our outflow, is equal to volumetrically our inflow. Okay, so we talked about this conceptually weeks ago. We proved it on Tuesday, and we're reproving it again here, just to kind of keep us abreast of, remind us how we get to this conclusion for these specific conditions using the material derivative and applying it to mass for a control volume system. Okay. All right. What I'd like to do next is, it's been a while since we've broken you up into groups to work a little bit. So I'd like you to take this problem and try to work on it in groups. So I'll randomly assign you here in just a moment. Given at the entrance, the channel velocity distribution is uniform with a value of V. It has a depth, you can see, of 0.75 feet. Downstream, the velocity profile is this equation. Given, so we've got some velocity profile here that's not uniform. The question is, what is V? So it's not, this is U over here. What is V in this situation? We're also given that the height now becomes 1 foot. So what I would recommend is a couple of things. One, you're going to have to deal with some dA here, right? We're going to apply the material derivative so that you can figure out mass coming in, mass flux in has to equal mass flux, or you can make this volume. Volume coming in has to equal volume going out. You need to get a mean velocity. In this case, V at the upstream end is your mean velocity. On the right-hand side, you're going to have to figure out what the mean velocity is for that profile. And then with your area, just assume the same width, right? 1 foot across or something like that. It just, there's no indication that it has changed width at all between these two locations. So the idea is that if you need to calculate an area, you could do this with just some width. You could call that B if you wanted and leave it constant. It might fall out, or you can just assume it's 1 foot. Okay, let me, the last thing that we will do here is so I'm going to put you all into breakout rooms to just work on this for 5 minutes. When you come back, we'll work on the solution together, and then I've got a couple of clicker questions for you. Okay, so there's my cursor. Right. Let's see, I think, how many of us are there? 74. Okay, let's go with 28 breakout rooms. Okay, so we'll see you guys back in a couple of minutes. We'll go about 5 minutes here.
Hi.
How's it going?
Good.
Good.
What if my breakout room is one with just 2 people and I'm not there?
Oh, well, you could jump
That's
in and
just-
give them a little
That's
advice.
true. That's true. I could do that. Probably should do that.
How's it going, Alexi?
It's going all right. Tired today. I don't know.
It must
Yeah.
be a warm day. I'm down in my basement and I can hear water coming down our downspouts outside, like just
I
this
can
like
get that too. Yeah.
flooding outside. Yeah, kind of cool.
Oh, you have snow on the ground right now? That's
But yeah, it snowed like 2
Yeah.
feet.
Yeah.
There's 2 feet of very heavy wet snow. It was
Yeah.
nasty.
Did trees like fall down or were they pretty?
Yeah,
Oh, gosh.
a lot of
Yeah.
branches fell.
Yeah. But no, I haven't seen any full trees fall down, so I think mostly just like big branches. And stuff.
Yeah, I haven't seen any full trees fall over, but yeah, a lot of branches. We have a lot of dead branches. Yeah, could be better. When did it last rain in Idaho?
It hasn't in a lot. We were just talking about this. My mom was just talking about this. It hasn't rained in a while. She showed up for our show. Yeah.
Hey
Hey, Ben.
guys, I'm actually in my breakout room alone. Is there any way you
Oh.
can put me in a different one, please?
Yeah, maybe. Let's see.
Oh, wait.
Wonder if I can assign you.
When I did them manually last semester, I could do that.
Yeah. Well, multi-pin. Put in waiting room. That's not what I want. Why can't I just move you? That's weird. All right, breakout rooms. Can I assign? Oh, you know what? I bet I could drag you over. Tell you what. I'm gonna move. I need to move Benedict over. It looks like he's by himself now. So I'll just do that randomly. And Ben, do you know which one you were in?
I think 22.
Okay. This one to 15. 22, 22. Oh, right. And you're not there now. Okay, so I'm going to move you to. Oh, you were supposed to be in there with Alexi. All right. I'm going to move you to 21. Okay,
Great, thank you.
you bet. Huh. I wonder. Oh, geez, is that a bigger problem? There's a couple of pairs. Okay, I shouldn't have made so many.
I make 3 per group or 2 per group or.
I was. Oh yeah, I should have just done 25. Somehow in my head, I was like, I thought we were going to end up with 5 in each room, and I thought, oh, that's too many. So, hey, Andrew, did you end up in a room by yourself?
So no, I actually was an idiot and scheduled an oral exam during this class. So I was in
okay.
earlier and then had to leave for a quick oral exam, not back.
Okay.
It's like everybody's in breakout rooms.
Yeah. Let me see. Okay, I'm gonna put you in room one.
Also, has there been any clicker questions that I might have
No,
missed?
not
Okay.
yet. We're gonna do them next.
Okay, sweet, thank you.
You bet. There you go.
My,
Students are so funny about clicker questions. Like, I feel like they're not going to change their grades at all. But like, I mean, if you don't go to any, it would change your grade. But like,
Yeah.
one clicker question, it's like so funny. I think.
Yeah. Well, they want the points where they can go. So.
Yeah.
Yeah.
It keeps
All
them
right.
motivated.
We don't have
Yeah,
a ton of
that's
time
cool.
left, so maybe I'll just go ahead and close the rooms and see if anybody can explain to us what they did here. I don't know. I don't have high hopes, but we'll see. I should look through this conclusion real quick. What's my solution here? Possible flow. Q in equals Q out. Yeah. Just integrating. Okay. All right. I'm going to close them all. Have everybody come back. So in 60 seconds, we'll all come running back. All right. Now people are slowly coming back. I'm not sure we're all back yet. Give folks another 30 seconds here. That was 20. Got a few folks still hanging out there. I think everybody gets kicked back to the main room when we get to the end of the minute here. So another 10 seconds. All right, in the meantime, did anybody come up with a solution to this problem? Did you come up with a number for V? Anyone? No one came up with a solution? All right, I forgot I gotta reshare here. Okay, so the solution to this one ends up, we start with just indicating that, sorry, I realize we're probably gonna go a couple minutes over time, so my apologies. All right, we're still in red. That'll, I gotta put pen. Okay, so, dang it. Come on, just give me pen mode. Okay, there we go. So Q at 1 has to equal Q at 2. And so we can say V times A1 is equal to some mean velocity at 2 times A2, right? And again, we said we don't know what the width is. So let's just go ahead and talk this through, the solution here. So V times A1 is equal to some integral over the cross-sectional area of the U that we're given on the right-hand side, the outflow, times dA, right? So this looks like the integral from 0 to 1 foot depth of the equation we're given, 4y minus 2y squared. And then I'm going to call the width B, and we're just going to take the derivative with respect to y, because that's the only thing that changes. For the dA, we just change with y here, okay? So y is height above the bottom, and B is width, okay? So B is constant, so now we end up with V times 0.75 feet on the left-hand side times B, that area then, is equal to, if we take this integral, we get 4 times B, let's just keep that in front as a constant, times 1/2 y squared, which we evaluate from 0 to 1, minus 2b times 1/3 y cubed, evaluated from 0 to 1 as well. And when we work this out, the b's will cancel here, so the width doesn't matter. And we end up with v times 0.75 feet is equal to 2 minus 2/3, which is equal to 4/3 essentially. Foot squared per second is what your units turn out to be. And V then comes out to be basically, 4 feet squared per second divided by 3 times 0.75 feet that I brought over. And if you do this math, you come up with 1.78 feet per second, which with significant figures looks like would come out to be 2 feet per second. But in any event, that's the solution to that one. Okay?
Professor?
Yeah.
If the bounds of the integral is the cross-sectional area, wouldn't it be like the bounds, shouldn't it be like 0 to B?
So it wouldn't be 0 to B. So we can, if we take B out of it, then we're just looking at the change with height, with Y, in that case. So we did have the original, you're right, we had it as dA. Because we're not given any information about some change in the, what I'll call the X direction going across the channel, only in depth, then we can just apply it to dy and pull that B out. Does that make sense?
Yeah, that makes sense.
Okay, Perfect. Okay, last thing here. An example of a deforming control volume is A, a jet engine, B, a solid pipe, or C, a balloon. What are we left with here, people-wise? We're at 60. Okay, it's like we lost a few. So let's see if we can, as soon as we get up to 60 or 57, I guess, I'll go ahead and stop it and we'll take a look at it. We'll save I have a second one, but we'll save that for Tuesday's class. All right. Do 3, 4, 5. We're almost there. Ooh, 58. Oh, interesting. Okay, we're at 60 responses. 61. Well, this is curious. Okay, let's take a look. All right, sure enough, the answer is C. Good deal. Had a couple of folks picking A and B. Maybe they weren't connected with us. Who knows? All right, you guys have a great weekend. As soon as this video is together, I will post it, the link to it on Canvas, and I'll send you an email when I get the new homework available, which will be ready or will be due in 2 weeks. So otherwise, I'll see you on Monday. Actually, we'll do recitation. So we'll
Really quick question.
Yeah.
So when you had it set up v times a1 and then equals the integral of u dA, did you do the integral to get the average velocity for u?
Yeah. Sorry. So I took the integral of the velocity of u to just give me the average, right? And then when I multiplied by the area essentially, or the I multiply. So I'm taking that with respect to y because that's the only thing I have. The b I throw out. I end up removing. Yeah. Does that make
Got
sense?
it. Thank you.
You bet. All right. Have a good weekend, everybody. Take care. Let's see. Did that work? I guess it worked. Wow. People scattered pretty fast.